You ever just stop and think about the invisible rules that guide a rushing river? Or the air that holds up a massive jumbo jet? Or, hey, even the blood that's flowing through your veins right now? Well, they all follow this kind of hidden script, a secret language. And today, we're going to learn how to speak it.
So, let's start with a little riddle. What do a pitcher's curveball, a huge airplane lifting off the runway, and a rocket blasting into space all have in common? I mean, they seem totally different, right? But what if I told you they're all playing by the exact same set of rules?
You guessed it, they all speak the secret language of fluid motion. And in this explainer, we are going to learn its three most basic, fundamental rules. We're going to follow a single drop of water on its journey, starting from a simple river and going all the way to a rocket engine. By the end of this, you'll be fluent.
All right, rule number 1 is actually something you already know deep down. It's a really simple idea called continuity, and it boils down to this. What goes in must come out.
Just picture this. You've got a wide, calm river, just kind of flowing along gently. Now imagine that river suddenly hits a narrow canyon. Every single drop of water from that wide part has to funnel through this tiny, narrow space. So what has to happen to its speed?
It's got to speed up, right? There's no other way. It's the only way for the same amount of water to get through a smaller area in the same amount of time. You can see this perfect trade-off right here. The area gets smaller and boom, the speed gets faster. It's a perfect inverse relationship.
And here's what that looks like in the language of physics. This is a simple take on the continuity equation. All it's saying is that the area of the wide part times its slow speed is equal to the area of the narrow part times its fast speed. You squeeze a fluid, it speeds up. It's really that simple.
And look, this isn't just some abstract thing about rivers. You use this all the time. Every time you put your thumb over the end of a garden hose to make the water shoot out further, that's continuity. It's the whole idea behind every nozzle, from your kitchen sink to a firefighter's hose. It even explains why blood has to flow faster to get through a narrowed artery. Okay, let's build on that with rule number 2. So if speeding up the fluid gives it more energy, the energy of motion, where does that extra energy come from? Because it can't just appear out of nowhere. This brings us to rule 2, the great energy trade-off. So to get this, you have to understand that a fluid's total energy is basically made of 3 parts. You've got energy stored in its pressure, you've got energy from its actual motion or its speed, and you've got potential energy from how high up it is. So let's go back to our river. When the water sped up in that narrow canyon, its energy of motion, its velocity, went way up. But since energy can't just be created out of thin air, where did that new energy come from? It came from its pressure. That's the core, the absolute essence of Bernoulli's principle. For a fluid that's just flowing along, its total energy, that's its pressure plus its speed plus its height, all adds up to a constant number. So in our flat river, when speed went up, something had to go down to keep the total the same. And that something was its pressure. The fluid literally trades pressure for speed. Faster fluid, lower pressure. And this isn't some newfangled idea. This was first described by Daniel Bernoulli way back in 1738. And then his buddy, the brilliant Leonhard Euler, came up with the math and the famous equation we still use just a few years later. So, why do we care about this pressure for speed trade-off? Well, it's a huge part of how airplanes fly. See, an airplane wing is shaped so the air has to travel faster over its curved top than its flat bottom. And what did we just learn? Faster air means lower pressure. So you get this zone of lower pressure on top of the wing and higher pressure below it. And that difference creates an upward push. Now, in reality, it's a bit more complex. The wing is also pushing air down. But this pressure difference is an absolutely critical piece of the puzzle we call lift.
Okay, so far we've just been describing how fluids behave. But our third and final rule, this is all about how we can actually use them to get work done. It's all about harnessing the fluid's push.
Imagine a super powerful jet of water shooting out in a perfectly straight line. It's got momentum, right? Now, what happens if we stick a curved blade right in its path? Well, the blade forces that water to change direction. And here's the magic. Because the blade is pushing on the water to change its direction, the water pushes back on the blade with an equal and opposite force.
This is basically just Newton's second law, but rewritten for fluids. It's called the impulse momentum theorem. And to put it simply, if you want to create a force, you have to change a fluid's momentum. The more you change it and the faster you change it, the more force you get back.
And that push is exactly what thrust is.
A rocket engine is just violently throwing hot gas downwards at insane speeds. It's a massive change in momentum, which creates that enormous upward force that lifts the rocket. It's also how a turbine in a hydroelectric dam works. Falling water gets redirected by those curved blades, forcing them to spin and generate electricity. And just like that, we've gone from a simple river all the way to a rocket.
So let's wrap this all up. We've just learned the 3 secret rules of the road that help us see all these invisible forces that are constantly shaping our world.
So remember, first, continuity. You squeeze a fluid, it has to speed up. Second, Bernoulli's principle. As that fluid speeds up, its pressure drops in a cosmic trade-off. And third, momentum. You change a fluid's direction and it pushes back, creating force. These 3 simple rules explain an incredible amount of what's happening all around us every single day.
From the way smoke curls up from a candle to the lift that keeps a bird hanging in the air, the world is constantly speaking this language of flow. So now that you know the basics, how are you going to see the world differently? What invisible forces are you going to finally see at work all around you today?